Thank you, Susie. I wanted to start by just thanking the organizers for the meeting for inviting me to what I personally have found a very fascinating meeting. I remember about 15 years ago, I was at a meeting in the US where we were bemoaning the lack of experiments and missions that we would look forward to about surveying the sky over the next 15 years. But just in the last few days, I've heard about technologies for gravity wave detection, about the next generation of ground and space-based missions that are going to come online in the next 2 years, about the opportunities for wide-field spectroscopy, and with Richard Ellis's talk, the synergy between the deep imaging surveys and the next generation of 30 and 40-meter class telescopes. And I think it really is, it feels like a special time to be part of astronomy. And if you'd, over the last 4 days, with 40 distinct presentations, papers, talks, and posters, you may have heard about one of these projects that's kind of come online, a project that has been under construction for the last 2 years, a project called the Large Synoptic Survey Telescope, or the LSST. And you would have heard about the work ongoing at the summit at Cerro Pachon in northern Chile, or the delivery of the primary mirror, or the first 2 science detectors that are coming from E2V and ITL. And if you'd spent, or if you'd actually been to some of these, one of these 40 talks, as we look at the last year of progress on the summit for the LSST, you would know that the LSST is an 8.4 meter telescope with a 3.5 meter secondary and a 5 meter tertiary. You know that the tertiary and the primary are built into the same substrate, the same O'Hara borosilicate glass. You realize that the telescope has a 3.5-degree field of view with an expected image quality of about 0.8 arc seconds, with a 3.2 gigapixel camera sitting on the top end of the telescope and a pixel scale of about 0.2 arc seconds. If you've been to the talks on the camera, you'd realize that the camera is actually 21 individual or independent cameras, each camera made up of 9 4K by 4K deep depletion devices. And the deep depletion devices enable us to detect the photons out to about 1.04 microns. As you can see here, we haven't just broken ground. After pouring about 6,000 cubic meters of concrete, the telescope is actually, or the mount and the facility is beginning to emerge from the ground. That the contracts for the dome and the telescope mount have been executed, that we are beginning to understand how our survey strategy will actually impact the science that we're going to get out of the project. And if we put all of this together, you realize that we're going to be surveying about 18,000 square degrees over 10 years, where each point on the sky will be observed about 826 times, reaching a limiting magnitude of about 27.7 magnitudes in the AB system, and detecting about 20 billion galaxies and 17 billion stars. If you've been watching the movie, you'd also realize that the weather last year was really terrible in northern Chile. So all of these things are true, right? Hopefully. But I want to give you a slightly different perspective on the LSST. And I was, in honor of Scotland's contributions to the culinary arts with the haggis and the deep-fried Mars bar, I thought that food might be a nice analogy. So if you remember when you were a kid and you were pouring your breakfast cornflakes into the bowl and you were reaching through that box of cornflakes with your grubby fingers looking for the free gift that came inside of the cereal box, you can think about the LSST as a box of computers with a telescope and camera that came for free, right? Now, with a telescope and camera that costs over $500 million and represents today about 1,000 person-years worth of effort, free is clearly a relative term. So why do I talk about it this way? Well, if you think about the telescope or the LSST 10 years into the survey, the computational power required to reproduce or reprocess all of the data and to analyze it requires about 140,000 to 200,000 compute cores. The computational power of this facility is about 1.8 petaflops in terms of scale. If you built that facility today, it would rank in the top 50 supercomputers in the world. And this means that software is becoming important. Software is important for the science. It's no longer a case of you just fix the problems in the hardware and the software. The quality of the science that you get out will be dependent on the analyses and the algorithms that we apply to the data. In many ways, the science that will come out of LSST will be limited by the camera or the telescope. It'll be limited by how we analyze the data. And you can see how this has changed in terms of the importance of software and algorithms over the last decade, or in fact, the last few decades. The first surveys of the sky, photographic plates, observed and analyzed by scanning by Shane and Wirtanen, by scanning the photographic plates by eye, counting the number of galaxies within 10 by 10 arc-minute pixels. The first really digital view of the sky with 1.6 million pixels. Took about 7 years to do this, another 13 years to publish it. But sufficient information to measure the distribution and the clustering of galaxies in the local universe. The distribution and clustering of galaxies that we use today to measure dark energy. The first digitized view of the sky was not from CCDs, but from the digitization of these photographic plates, either using the automated plate measuring machine that you see here, or the Cosmos and SuperCosmos plate scanners you can find up the road at the ROE. Producing 0.5 arc-second pixels, but generating the first terapixel view of our sky. Doing this with about a single processor, 200 megahertz Pentium processor. As we move to the linear universe with mosaic cameras and the CCDs, we didn't actually increase the number of pixels or the size of the surveys that we were doing, but instead the data rates grew enormously by an order of magnitude. And this led to the first generation of dedicated software pipelines to process the images. And now where we get today with sensors at the scale of the LSST, and this shows you a simulated image of a single image from the LSST camera, the 3.2 gigapixels. The mottled view you see is the variation in the bias level from each one of the amplifiers. And so today, we get an order of magnitude, a 20-fold increase in data rates over the SDSS. And this means we need dedicated pipelines, and these pipelines, and I counted these up before I came out here, over 1.1 million lines of code currently being written to analyze the LSST data. And the power of this is that we will get images that look like this. This is from the Hyper Supreme camera on the Subaru telescope. But images like this, not just for, and images to this depth, not just for a fraction of a degree or a few degrees on the sky, but for 18,000 square degrees over the sky. Now, processing these data is actually a daunting task. This shows you a simulation of the expected survey simulated survey for the LSST. Each point represents a position, a visit, an observation on the sky. Each visit, 2 back-to-back 15-second exposures, and then a 6-second slew of the telescope to another 3.5 degrees across. Coming back to the same point on the sky every 15 to 60 minutes, and that enables us to detect moving sources. 826 visits per point on the sky. The color of the point corresponds to the filter in which the visit will be observed. One of the U, G, R, I, Z, and Y filters that are part of the LSST. The movie itself has been sped up by about a factor of 2,000, but this means that we'll be generating about 15 terabytes of imagery every night. And the life of one of these images or one of these visits is a second for the shutter to open across the camera. 15 seconds of exposure, another second for the shutter to close, 2 seconds to read out this camera, 4 seconds to transfer the data from northern Chile up to Illinois where it's processed, 5 seconds to uncompress the data, 8 seconds to flat field and biosubtract it, 24 seconds to find anything that has changed or moved or varied, and then 16 seconds to associate that object with every other observation that has been undertaken with the LSST prior to that time, package it up, and release it to the community. 10,000 alerts or variable sources detected every visit. 10 million variable sources or moving sources detected every night, released to the community within 60 seconds of the observation being taken. And there's many interesting aspects about distributing these processes and the data across the 150,000 cores at the end of the survey. But what I want to focus on are the algorithms, and the algorithms that have changed our understanding and enabled new science to come out of projects like the LSST. So if you take two images, each image has a point spread function associated with it. If you can compare these two point spread functions, you can work out how to map one point spread function to the other, how to map the image quality from one image to the next. An algorithm that was developed by Allard and Lupton in the 1990s, an algorithm that allowed us to do systematic image subtraction to enable us to find sources, the supernova that's residing next to its host galaxy, and to do this at scale, rather than just blinking the images that we used to do. But because we don't understand everything about the atmosphere, or the performance of the telescope, or the optics, then not every source that you detect is an astrophysically interesting object. Here I show you a couple of the first two images, and what happens when you subtract one image from the other. We get artifacts. If we look at the success rate, the number of false positives to real sources that we find in telescopes like the PTF, the Palomar Transit Factory, it's factors of 20 to 100 to 1. If you're getting 100 to 1 false positives to every object that you detect, and you're detecting 10 million alerts or variable sources every night, you can see this is going to be something of a challenge. And so algorithms, and in particular machine learning and classification algorithms, have transformed the science that we can get out of these time domain surveys. An algorithm that was used for the Palomar Transit Factory, an algorithm that's for classification that is known as the random forest. An algorithm that doesn't classify objects into RR Lyrae or Cepheids. It classifies objects into real versus bogus, real objects versus errors. Changing the 100 to 1 false positive to real astronomical events to 2 or 3 to 1, enabling projects like the Palomar Transit Factory to discover the supernova 2011 FE. The quickest or the earliest that we have actually observed a supernova after its explosion, enabling us to study events like shock outbreaks. Or the supernova 2007 BI. The introduction and the discovery of superluminous or ultraluminous supernovae. These ultraluminous supernovae that really have transformed our understanding of the supernova physics. It's the algorithms that enable the science. Recent work from the LSST has begun to show that if we understand the noise within the system, we can perform as well as these machine learning techniques in terms of reducing the number of false positives. So we're now reaching a regime where, much like Martin Hendry's talk, when he talked about the gravity wave detection, if we understand noise and we understand the properties of the noise and how those properties get correlated by all of the observations and the operations that we do, we can begin to extract out these astrophysically meaningful sources. And that means that the machine learning algorithms that we can begin to use now can begin to classify on whether it is a Cepheid or a variable or something interesting that we should follow up with another telescope. A second algorithm, if you have 826 observations of the same point on the sky, you want to be able to combine them. If we take our existing software pipelines, like the Sloan Digital Sky Survey, we subtract out the sky background to find stars and galaxies. And this is a very powerful technique. It's why the Sloan was so successful in terms of the number of papers it's generated. But you can see here that these operations that we do can actually also subtract out the wings of the galaxies. biasing the results, biasing our analyses, biasing even the cosmological measurements that we can estimate from the data. But with new approaches, this shows you the SDSS image for a single image on the equator, on stripe 82 for the SDSS, and then a new algorithm that takes into account, it separates out the astrophysical sky from the scattered light. And by subtracting out the scattered light and not the astrophysical sky, as we co-add these images, you can now see we don't just detect the stars and galaxies, we detect the nebulosity. And this means that the science that can come out of these pipelines, like the LSST, is much broader. It's not just measuring the properties of stars and galaxies in the distant universe or the faint universe. It's being able to see the large-scale structure of the gas within our own galaxy. There are 36 CCDs all combined within this image, and you can't see the seams between any one of them. So the LSST, through these algorithms, through this analysis, will process about 15 terabytes of data per night. 10 million events detected, 6 million moving sources within our solar system. By the end of 10 years, it will achieve about 37 billion objects, 20 billion galaxies, 17 billion stars. The total numbers are still in flux as we determine how much time we spend in the galactic plane versus outside of the galactic plane. All of these data stored, processed, archived, and made available to the users. Often when we talk about this, we talk about it as an era of big data. And it's not just astronomy that talks about big data. It's the same things in biology, in neuroscience. We talk about how we're becoming overwhelmed by data and how the data that we're collecting is going to transform the science that we're going to be able to do. But I think we focus too much on the volume of the data. I mean, I did the same thing myself when I talked at the beginning. 20 billion sources, 20 billion galaxies, 17 billion stars. You know, petabytes of data being generated. It's not the amount of data that you're collecting, it's the amount of information that you can extract from those data. So if we look at what today the companies like Amazon and Microsoft and Google are doing, there are 1.7 million likes on Instagram every minute of every day. That means 1.7 million people interacting with data every minute of every day. YouTube uploads 300 hours of video every minute of every day. That means if you take that for the whole year, that's about over 400 petabytes of video if those videos were in high definition. So that, even that would give the square kilometer array a run for its money. So the question isn't about how much data you're collecting. It's about, in terms of the videos, which videos do you really want to see? Now, you may laugh, right? But if you're searching for a cat licking a lollipop and you come across a movie of the LSST, you're not going to be happy, right? The science that you want to do is not the science that the person next to you wants to do. Right? The science that you want to enable with projects like the LSST means extracting information from these data. It means understanding the data. We talk about the volumes of data that we're achieving. Data in astronomy doubles every year. We get spikes in this relationship when new surveys come online. The compute power doubles every 18 months through Moore's law, whether you're thinking about this in terms of transistors or number of cores, the computational power that we have for the same effective cost. The difference between these two lines we make up for using large parallel systems, the 140 to 200,000 cores that the LSST will use to process its data at the end of 10 years. It's the fact that they track each other that enables us to do the science like LSST or like the square kilometer array. But what is less well understood or appreciated is that our ability to make sense of the data, our human cognitive capacity doesn't double every year. Right? For those of you on Twitter and Facebook, you may question whether it increases at all. Right? But if we can make sense of the data, there's an opportunity to extract more information and more science than you would naturally think. So I wanted to end with an example that comes from the Pan-STARRS telescope. Pan-STARRS, a 1.8-meter telescope, a 1.4 gigapixel camera. You can see this beautiful image from Pan-STARRS with the lagoon and the Trifid Nebula. You can see the beautiful dust lanes that go across the Pan-STARRS, across this image. Greg Green and collaborators recognized that by detecting the stars within the Pan-STARRS data, 800 million stars, and by looking at the colors of those stars in the G, R, I, and Z passbands, so G minus R, R minus I minus C, that they could estimate the brightness and the type of that star. And when they could estimate the brightness and the type of the star, they could estimate its distance. And when they've got the estimate of the brightness and the type and the distance of the star, then they could estimate the reddening, or the amount of dust. And because they could do this on a star-by-star basis, even in a statistical sense, they could calculate the amount of dust within the Milky Way, not just projected on the sky, like we've seen from the Schlegel, Finkbeiner, and Davis dust maps, but now in 3 dimensions. So what I'm showing you here is a reconstruction of the 3-dimensional distribution of dust within our galaxy done by Greg Green and his collaborators. And you can see as we zoom in towards Orion, this distribution of dust in 3D uncovers rings of dust in the radial direction, that you wouldn't be able to see just from the projection. So if you think about this, this is 800 million stars for which we've measured the positions and the colors on the sky. A 2D projection of colors, of sources on the sky, and recovering the 3-dimensional distribution of dust within our own galaxy. With 17 billion stars from the LSST, think about the resolution that we could achieve with maps like this. So the LSST has 4 main science themes: to understand the transient universe, the supernovae, the gamma ray bursts, potentially following up gravitational wave detections; to uncover a census of our solar system, the outer, the Kuiper belt objects, the near-Earth objects; to measure structure within our own galaxy in measuring the tidal streams that you see in NGC 5507; measuring dark energy from gravitational lensing. Each of these science questions maps directly onto the algorithms and the machine learning and the statistical techniques. So the transient universe is anomaly detection. Creating a census of our universe are tracking algorithms, the same algorithms that people use for tracking people or tracking missiles across the sky. The measurements of structure within our own Milky Way, a density estimation and clustering. The nature of dark energy through gravitational lensing is image processing and data-intensive analysis. There's a direct mapping between the science that we want to do and the algorithms that we need to apply. So the future is bright, right? The future, first light for LSST in 2020, operations in 2023. With the development of the algorithms that we have for processing the LSST data, we're now seeing that the software is what's going to determine the science that we can achieve with the LSST. We're seeing that software becomes important in terms of what science the LSST can uncover, whether it's dark energy or the solar system or the Milky Way or just looking at the transient universe. But as everybody in this audience knows, that to study instrumentation takes resources. And resources don't mean hardware. It doesn't mean compute power. It means the people who can understand and work with the data. The people like Greg Green who can think about the data in different ways and extract more information than you would naturally think just from looking at the distribution of stars on the sky. And so Hitoshi started the first plenary session, or ended the first plenary session, with an advert. So I thought it's appropriate that I end the last plenary session also with an advert. And what I wanted to advertise is the LSST's Data Science Fellowship Program. It's a program that was created by the LSSTC. This is the LSST Corporation. It's aimed at graduate students. It's a 2-year program to teach graduate students about the skills that they need to do the science of the LSST when you're working with data sets that are billions of sources and petabytes in size. It's a training program that will last, as I said, for 2 years through a series of schools with a cohort of like-minded students. If you're interested in hearing about this in any more detail, I'd be very happy to talk to you afterwards. And with that, I'll thank you.